Hello. Today we are working on the Chapter 6 review over rational functions. In section 6.1 we talked about inverse and direct variation. If you are given an equation, well, a couple things you need to make sure you know is that inverse variation, if you're looking at the equation, y equals a over x, or a divided by x. So that's the equation or formula for the equation for inverse. If it's direct variation, then y equals a times x, where a is just a number. So some textbooks use k, some textbooks use a, but a represents a number. So what you want to do with these first equations is solve for y. So if you get y by itself, you would have to divide both sides by the 4x. So when you divide both sides by 4x, you get y equals 2 over 4x. So again, the x is in the denominator. Even though it doesn't look exactly like the y equals a over x, we could take 2 divided by 4, which would then give you reduce to 1/2, or 0.5 over x. So this, because your variable x is in the denominator, it is inverse. The next problem here, number 2, you have to again solve for y. So when you solve for y, you got to divide by 7 on both sides, and it's the x now you can see is in the numerator. So again, even though the 2/7 is doesn't look exactly like the a times x, because the x is being multiplied, you could rewrite this as 2/7 times x, but again, y is by itself. 2/7 times x, or 2x over 7, this would be direct. And basically, so when you're given these equations, solve for y, and it should just be a single fraction. If the x is in the denominator, then it's inverse. If the x is in the numerator, then it's direct. It's kind of an easy way of doing it. The other thing that you might be given is a table. So if you're given a table, you're asked to determine if it's direct or inverse, you basically are looking to see whether that constant of variation is a product or a ratio. So in inverse variation, a is going to equal y times x, or x times y. In direct variation, a is going to equal y divided by x, or a constant would have so the a value in direct would be y's divided by x. Inverse, the a value would be y times x. So if you find the product y times x, you're going to get -56 every time. So if you look at your table and multiply x and y values together, you get what we call a constant product. If you were to divide the y by the x, so 28 divided by -2 would be a -14. -4 divided by 14 would be a -2/7. So the ratio would not be the same. So if you got a common product right away, common product means that it's going to be inverse. So the product is inverse. The ratio is direct. So if you can take all of your y values and divide by the x values and get the same thing, so that's what we did here. 16 divided by -4 is -4. 25 divided by -5 is -5, but they're not the same. And when you multiply the 16 and the -4, you get -64. And if we multiply, the products are not the same either. So if there's no common product and no common ratio, then it would not be direct or inverse, so it would be neither. And then the last table here is written horizontally, but again, it doesn't matter. If I took my y's times my x's, I would not get the same thing. I can just check that right here. If I multiplied, I would get 12, and I multiply here, I'm going to get 75. But if I divide y by x, 27 over 81, 4 divided by 12, 2 divided by 6, and 5 divided by 15, I would get the same. It would simplify to 1/3 every time. So there would be a common ratio. So that means that these points have a direct variation. All right, so hopefully that helps you understand the difference between direct and inverse. If you're given an equation, solve for y and look to see where the x is. If it's being divided, it's inverse. If the x is in the numerator, it's direct. But when you are given y's and x's, if there's a constant product or a common product, it's inverse. If there's nothing in common, then it's neither. If it's a common ratio, then it's direct. So the other things that we did in first section is rote equations. So if they're telling you, if you're given that the time in hours that a vehicle can travel varies inversely with the speed s in miles per hour that the vehicle travels, then the distance, then you know that t or time equals something divided by s. Well, that something here, that's our a value. So to find a, you have to take an example that they give you. Oh, they tell you the distance between Northwest Indiana and Orlando, Florida is approximately 1,200 miles. So that's your a value. So if you take the time times the speed, the time in hours times your average speed, you would get the total miles that you traveled. So that's one way, that's your equation. So we wrote the equation to represent this situation. Now, what they're asking you to do is basically use the equation. What would a vehicle average speed need to be in order to get to Orlando, Florida in 15 hours? So the time would be 15. So depending on what you're given, that's what you're going to plug things into. So if I'm given 15 hours and I want to know what speed, I can, like a proportion, can switch the numerator here with the denominator here and get s equals 1,200 divided by 15, which gives me tells me that I need to travel at 80 miles per hour, and that's my average, in order to get there in 15 hours. So that's pretty fast. Not sure that you would make it within 15 hours. All right, so that's a quick review of inverse variation and direct variation in section 6.1. If you still don't understand some of these things, I would go back to your notes for 6.1 and maybe the quiz review that had a lot of good problems on it. All right, 6.2. So in 6.2, we were graphing. We started graphing rational functions. So in this rational function, we have -5 over x plus 6. So when you have a fraction with a plus or minus after it, we were using h and k to figure out your vertical asymptote and your horizontal asymptote. So this plus 6 is going to shift the graph up 6 spaces. So that's going to shift your horizontal asymptote from y equals 0 to be y equals 6. However, there's nothing being added or subtracted to the x, so your vertical asymptote would just be 0, or whatever is going to make that denominator 0. So then your domain, all real numbers except for x equals 0. Range, all real numbers except for y equals 6. So that's where we get our horizontal line and our vertical line. So this is, again, our horizontal asymptote at y equals 6. This is our vertical asymptote at x equals 0. All right, so how do we get these other points? One step at a time. All right, so to find your x-intercept, you basically take the whole equation and set it equal to 0. Whoops, that's, where did I find that? Oh, here it is. Okay, I'm like, where did I, yeah, this big arrow that's showing how I got this, yeah. So you take this -5 over x plus 6, set it equal to 0, and then solve for x. So if I subtract 6, I would get -5 over x equals -6, then divide by x to get it out of the denominator. That would give me -5 then equals -6x, and then divide by -6 and simplify, you get 5/6. So 5/6 is your x-coordinate, 0 is your y-coordinate. As far as the y-intercept, usually you would substitute 0 for x and then simplify. But if you try to divide by 0, you're going to get an undefined value. So there will be no y-intercept, or y-intercept will be none. Then you want to find some additional points that are to the right and to the left of your vertical asymptote. So since our vertical asymptote is at 0, we're going to plug in numbers like -1 and -2, and then +1 and +2. So if you plug in -1 into your original equation, so -5 then gets divided by 11, I'm sorry, -1. So -5 divided by -1 would be 5, plus 6 would be 11. And then when you plug in -2 for x, you would get 2.5 plus 6 would give us 8.5. And then on the right side, you would plug in a 1, which would give you -5 plus 6, which is 1. And then if you substituted 2 for x, you would get -2.5 plus 6, which would be a positive 3.5. So graphing my x-intercept at 5, 6, 0, graphing my 1, 1, and my point 2, 3.5, my point -1, 11, which is way up here, and -2, 8.5, and using my asymptotes to help guide me, you would have this branch here of the hyperbola and this branch of the hyperbola right there. All right, so hopefully that made sense. Moving on to the next problem. We have another graph, but this time we have an h and a k value. So again, it's just a constant in the numerator, x minus 4, so x cannot equal 4, so therefore the vertical asymptote is going to be x equals 4. Because we have this +1, that means the graph is shifting up one space, so your horizontal asymptote is going to be y equals 1. So here's your horizontal asymptote at y equals 1. And here's your vertical asymptote at x equals 4. So then your domain, all real numbers except for x equals 4, and all real numbers for your range except for y equals 1. To get your x-intercept, again, take that whole thing and set it equal to 0. Subtract 1, and then multiply both sides by the x minus 4. Then subtract your 4 and divide by -1, and you get x equals -2. So that is your x-intercept. To find the y-intercept, you substitute 0 for x. But this time, when you put 0 in for x, you do not get an undefined value. You're going to get 6 divided by -4 plus 1, which will give you -1.5 plus 1, or -0.5. But I have a positive there, so that should be a -0.5. Yeah, so here it is graphed at -0.5, but here I didn't have -0.5 written. All right, so I've got my horizontal asymptote again at y equals 1, my vertical asymptote at x equals 4. I've got my x-intercept at -2, 0, my y-intercept at 0, -0.5, and then I'm going to just find some extra points that are to the right and left of 4. So I'm going to plug in -3 and -2, and then +5 and 6. Or not -3, +3 and 2, and 5 and 6. All right, so here's my equation. If I put 3 in for x here, 3 minus 4 would be -1. 6 divided by -1 is -6, plus 1 is -5. I got these mistakes all over the place. So 3, -1, 2, 3, 4, 5 should be here. Yeah, so that point was a little bit off. And then if I substitute 2 for x here, 2 minus 4 would be -2. 6 divided by -2 is -3, plus 1 would be -2. So the point 2, -2 is right there. Substitute 5. So again, 5 minus 4 would be 1. 6 divided by 1 would be 6, plus the 1 would be 7. So then graph the point 5, 7, and then substitute 6 in for x. So 6 minus 4 would be 2. 6 divided by 2 would be 3, plus 1 would be 4. So then we graph the point 6, 4. And then we draw our branches of our hyperbola, and that's the rest of our graph. All right, now we have some graphs that do not have, so the equations look a little bit different. Here we have a constant in the numerator, and then we have x plus or minus something, and then plus or minus something here, so we have an h and a k value. Well, here we have a numerator where the x is in the numerator and in the denominator. So these are not your, what they call simple rational functions. But again, looking at the denominator, your x cannot equal 1, so your domain would be everything except for x equals 1. But your vertical, so the denominator does tell you what your vertical asymptote is going to be. So your vertical asymptote is going to be x equals 1. If you set your numerator equal to 0 and solve, that's how you find your X-intercept. So your X-intercept, if I take just the numerator, so for these, when you're finding the X-intercept, you don't have to set the whole thing equal to 0 like we did in this one. Here we have to set the whole thing equal to 0. If we set this whole thing equal to 0 and then multiply the denominator on both sides, that denominator is just going to disappear. So it's not necessary to multiply the whole thing equal to 0, just the numerator. So if you take your numerator and set that, so I did show how down here, if you did set the whole thing equal to 0, you and multiplied by x minus 1, that 0 times x minus 1 would just be 0. So really it's just the numerator that you need to set equal to 0 and solve, which then would give us 3/4. So 3/4 is our X-intercept, and here it is on our graph. To find your Y-intercept, you still want to substitute 0 for x. So if we substitute 0 for x, we're going to get 0 minus 3, or negative 3 at the top. 0 minus 1 is negative 1 in the denominator, and divide, we get positive 3. So the point 0.03 is right here. My vertical asymptote was 1. X equals 1, my horizontal asymptote, y equals 4, and again, where do we get that from? So there's 3 rules for your horizontal asymptotes. If the degree of the numerator, which in this case is 1, is the same as the degree of the denominator, which is also 1, then your horizontal asymptote will be y equals the leading coefficient of the numerator over the leading coefficient of the denominator. So the leading coefficient of the numerator is 4. The leading coefficient of the denominator is 1. 4 over 1 is going to be 4. So there's our horizontal asymptote. And then using the x and y intercepts, we can graph that branch. But then we do need to plug in a point to the right, a couple points to the right. It looks like I did plug in a -1 to the left just to kind of have another point to graph. But if you substitute 2 and 3, again, 2 and 3 are to the right of 1. And I substitute those in, I get 5 and 4.5. So that gives me the point 2, 5, and then 3, 4.5. So then I can connect those and use my asymptotes to guide me, and I get my graph. All right, so that's that one. And then the last graph, oh no, I think this is the second last. Anyway, the next graph. So again, we have a linear polynomial at the top, a linear expression at the bottom. So since the degrees are the same, your horizontal asymptote is going to be y equals the leading coefficient over the leading coefficient, which in this case is 2 over 2, which would just be 1. If I set my denominator equal to 0 and solve, I would get a -1/2. So that's my vertical asymptote, x equals -1/2. If I set my numerator equal to 0 and solve, or in this case I set the whole thing again equal to 0 and solve, but you really just need to set the numerator equal to 0 and solve, you would get x equals -3, so that's your X-intercept. As far as domain and range, again, all real numbers except for what your vertical asymptote is, so except for x equals -1/2 and y equals 1. All right, so as far as finding the y-intercept, again, you substitute 0 for x. So if we plug 0 in for x, the 2 times 0 plus 6 would just be 6. 2 times 0 plus 1 would just be 1. When you divide, you get 6. So that gives us our y-intercept of 0, 6. All right, so now we go to the graph. So your vertical asymptote, x equals -1/2, is just a half a space to the left. I always make a dotted line. Your horizontal asymptote, y equals 1, so crossing the y-axis at 1. Your x-intercept at -3, 0 is right here. Your y-intercept at 0, 6 is right here. So we do need at least one more point on the left and right side of our vertical asymptote. So since it's at -1/2, you can plug in -1, you can substitute -2. So I did both. If you substitute -1, you end up getting -4. If you substitute -2, and you get -2/3. So here's my origin. So -1, -4 is right there, or -2, -2/3. So all those 3 points using the asymptotes to guide you will give you that half of the hyperbola. And then 0 I already had, but then 1, if I substitute 1, I get 8/3, which if I divide would be 2 2/3 or 2.7. So go over 1 and up 2.7 or 2 2/3, and then draw that part of the graph. Okay, moving on to number 11. So in number 11, we have a graph that's a little bit different here. So this time we're not going to have a horizontal asymptote. And again, that goes back to those horizontal asymptote rules, where if the degree of the numerator, which in this case is 2, is bigger than the degree of the denominator, which in this case is 1, then there will be no horizontal asymptote. So we would just say none for the horizontal asymptote. Your vertical asymptote, however, is setting, if you set the denominator equal to 0 and solve, you would get -2. So x equals -2 is your vertical asymptote. If we set our numerator equal to 0 and solve, we would have to add 9 and then take the square root, which would give us 2 x-intercepts. So we'd have an x-intercept at +3 and another one at -3. So there's the x-intercept at -3 and at +3. So -3, 0, -3, 0. For your y-intercept, you're going to again substitute 0 for y. So that's what I did here. So I just put it in the table. I didn't make it a separate place, but I substituted 0 for y, and then simplified and got -9/2, which is -4.5. So then again, where do we get these other values? Well, if your vertical asymptote's at -2, plug in -3, plug in -4, but we already had -3, 0 was one of our x-intercepts. When I substitute -4, I got -3.5, and then so you can see it's going to get closer to the asymptote as it's going up, and as it's going down, it's going to go away from. And then we have our y-intercept at 0, 4.5, but if we substitute -1 into our equation, we get -8. So -1, -8, and then we also have our x-intercept here. So those 3 points, it's going to go away. So it's going to get closer as it's going down it's going to get closer to the vertical asymptote as it's going down, and then farther away as we go to the right. All right, so again, that's a graph that has a leading or degree on the top that's bigger than the degree on the bottom, meaning there's no horizontal asymptote. Okay, and then the next one here, we didn't necessarily have to graph it. We just had to state the vertical and horizontal asymptotes and the x-intercepts, if there were any, the y-intercept, and domain. So again, we have a degree. Looking at the degrees, the degree on the top is the same as the degree on the bottom. So then we go to leading coefficients, 1/1. That's where we get the 1 from here. So since the top degree is equal to the bottom degree, your y equals leading coefficient over leading coefficient, so that's there. For your vertical asymptotes, you would factor your denominator or set the denominator equal to 0 and solve. Let me see where I have that. Oh, well, I ended up factoring. But if you factor the denominator, x squared minus 4 factors into x plus 2, x minus 2, so then negative and positive 2 are your undefined values, which means your vertical asymptotes, there are 2 of them, x equals +2 and x equals -2. If we set our numerator equal to 0 and solve, so factoring it would help, and then if you set that equal to 0 and solved, you would get x equals -3 and x equals +1. So that's what I have here. Set the numerator equal to 0 and solve. But again, I factored it to solve it, and I got -3 and +1. So again, there's two x-intercepts, -3, 0, and +1, 0. In order to find my y-intercept, I substituted 0 for x, and you can substitute it into this equation, or you can substitute it into this equation. This one would actually be easier because all of these x's would make these terms 0, so you'd end up just getting -3 divided by -4, which is a +3/4. If you were to substitute 0 in the factored form, you would still get -3 divided by -4, which again is 3/4. So with this one, you didn't necessarily have to graph it, just had to state your vertical and horizontal asymptotes, domain, no range, I guess, x-intercept and y-intercept. All right, so in number 13, I do just reviewing what those horizontal asymptotes were again. So the rules for horizontal asymptote: if the degree of the numerator is less than the degree of the denominator, then the horizontal asymptote is y equals 0. So we didn't have really a whole lot of examples of that. So you can always, on this review, but there were a lot of good examples of that in the notes for 6.2, also the quiz review. The next scenario is if your degree of the numerator is equal to the degree of the denominator, then the horizontal asymptote is y equals the leading coefficient over the leading coefficient of your numerator and denominator. And then the third rule for horizontal asymptote was that if the degree of the numerator is greater than the degree of the denominator, then there's going to be no horizontal asymptote at all. All right, then we got to section 6.3, which we started simplifying, multiplying, and dividing. So always remember to factor first when you have binomials or trinomials. So if you have something like x to the third plus 27, where you have a perfect cube plus another perfect cube, or a perfect cube minus a perfect cube, then you have to factor that using the sum of cubes formula, where you take the cubed root of x to the third, which is x, the cubed root of 27, which is 3, and then the sign here is the same. So if you need to look back at the formula for your sum of cubes and difference of cubes, then you need to do that. That should be in the notes for 6.3. But the sign here is going to be the same. So a sum of, going back just a second, the sum of cubes or the difference of cubes always factors into a binomial and a trinomial. In the binomial, the sign will always be the same as what you had to begin with. And then the sign in the trinomials the first sign here is the opposite of what that one was. The last sign is always positive. So we use the acronym SOAP, same, opposite, always positive, as what you had here. And then to find this value and that value, you just take the cubed root of this, which is x, the cubed root of that, which is that. And we call those a and b in the formula. So in the formula, this is a squared, but instead of a, we take x and square it. In the formula, it's a times b, but again, it's x times 3 or 3x. In the formula, this is b squared. Well, our b is 3, so 3 squared would give us 9. The denominator here, we cannot factor out a 3, and since there's a leading coefficient of 3, we're going to need to use the AC method. So I worked that out down here. I'm going from 3 terms to 4. My first term, 3x squared, would stay the same. My last term was -3. That would stay the same. But then multiply your a and c together, which gives you -9. So now we need two numbers that multiply together to equal -9, but add up to +8. So, add up to +8. The way I word it, though, I try to think of the numbers first. Two numbers that multiply together to equal 9 that subtract or have a difference of 8. So that's where I get the 9 and the 1 from. But because the 9 is negative, I know my signs have to be different, and that 8 is positive, so the larger number needs to be positive. So positive 9x and negative 1x would be how we got that positive 8x in the middle. All right, so then we factor by grouping, factor out a 3x, factor out a -1, factor out the x plus 3, and the 3x minus 1 goes together. So that is now the denominator here. So the only thing we can reduce is the x plus 3's, which will then give us x squared minus 3x plus 9 over 3x minus 1. Now, if you were asked to state your domain or your undefined values, you would say x cannot equal -3, and a positive 1/3. All right, the next one here, we have a binomial at the top, a monomial in the bottom. So always factor binomials and trinomials. So what can we factor out? We can factor out a 5, and we can factor out a x to the third. So when I factor out a 5x to the third from both of those terms, I get 3x minus 5. The denominator is just 10x squared. I'm going to leave that the same, but then I'm going to factor this out a little bit. You don't necessarily have to, work this out completely like I did, but the 5 and the 10 or 10 has a factor of 5 in it, so the 5's can be reduced, but there'll still be a factor of 2 left over. Your x to the third can be factored into x squared times x, so the x squareds reduce, and there's an x left over in the numerator, and then your 3x minus 5 is still left over in the numerator. So we've got x times x, 3x minus 5 over 2. And leave it in factored form. You do not need to multiply that x into that binomial. All right, the next one, we're finding the product, and it's all monomials. So when you have all monomials, there's a couple different ways you can go about attempting this, or, we could reduce some of these right away and then multiply across, but for explanation purposes, it's probably just easier just to multiply across then reduce. So 12 times negative 5 would be negative 60. 10 times 3 would be 30, and then when I reduce that, I just get negative 2 because 30 would reduce from both the numerator and denominator. Then I would, when I'm multiplying variables that are the same, you add your exponents. So 2 plus 6 would be 8, 11 plus 5 would be 16. I don't have any a's, so the a to the 10th will stay the same. B to the first and b to the third would be b to the fourth. All right, so then you can either factor or just subtract. 8 minus 10 would be negative 2, so you have to have an a squared at the bottom. 16 minus 4 would be 12, so you have a b to the 12th at the top. The other way to do it is to factor it. So if I factor my a to the 10th into a to the 8th times a squared, the a to the 8th can be factored or reduced. And then b to the 4th and b to the 4th, so the b to the 16th factors into b to the 4th and b to the 12th, so I can reduce the b to the 4ths. Notice that the way that I factored this was different because these are all monomials. The vertical factoring we can only really use when it's monomials. So like here we had monomials, so we reduced vertically. But otherwise you have to have in order to reduce a binomial, you have to, the whole binomial has to be at the top and the bottom of the fraction in order to simplify it. All right, so next. Okay, so hopefully on your copy this has been corrected, but this should be a plus 56 here. So we're multiplying again, but we've got a trinomial. So whenever you have a trinomial or binomial, again, you need to factor those. So that trinomial in the numerator here can be factored into x minus 8 and x plus 2. This 10x squared, I just left it alone. Here, this binomial, factor out a greatest common factor, so I can factor out a 2 and an x, which then will leave me with x squared minus 49, which can also factor in the next step. The x squared minus 15x plus 56 factors into x minus 7 and x minus 8. So at this point, I can reduce, so this is basically like one fraction now since we're multiplying. Anything from the numerator can be reduced with any factors in the denominator that are the same. So this binomial, and binomial factors can only be reduced if they're exactly the same. So x minus 8, x minus 8. One's in the top, one's in the bottom, so they can be reduced. Now here, I didn't necessarily break down the 10 and the x squared, but 2 and 10 can be divided by 2, or both have a common factor of 2. So the 2 would cancel out, the 10 would become 5. And the x and the x squared I can reduce by x, which will still leave me with an x left over here. So I still have the x plus 2 at the top. I still have the 5x here on the bottom. The x squared minus 49 is a difference of squares, so that would factor into x minus 7 and x plus 7. And then I've got this x minus 7 from the denominator here that I brought down. But the x minus 7s can reduce, so what I'm left with now is x plus 2 and x plus 7 in the numerator and just 5x in the denominator. All right, so here's another one where we're factoring. This is a basic trinomial, can be factored into x minus 2 and x minus 3. This x plus 2 cannot be factored. And then this one, this trinomial, I'm going to factor using the AC method. So the 2x squared stays the same, the plus 10 stays the same. Multiply my a and c, which gives me a positive 20. So two numbers that multiply together equal 20, that add up to 9, 4, and 5. So it's going to be a positive 4x and a positive 5x that give us that positive 9x. And then I'm going to factor by grouping. So factor out of 2x, which gives you x plus 2. Factor out of 5, which also gives you x plus 2. Factor out the x plus 2, and then put the 2x plus 5 together. So those are the factors of that numerator. The denominator, again, we've got a difference of cubes. So difference of cubes, just like the sum of cubes, is going to factor into a binomial and a trinomial. The x comes from taking the cubed root of x to the third. The 2 comes from taking the cubed root of 8. And the sign in the binomial is the same. In the trinomial, this sign is opposite, and the last sign is always positive. We get the x squared from taking this x and squaring it, the 2x from multiplying the 2 and the x together, and the 4 from taking the 2 and squaring it. So now the x plus 2, the x plus 2 here on the top can reduce with the x plus 2 in the denominator, and the x minus 2 on the top and the bottom can cancel, so we have x minus 3, 2x plus 5 in the numerator, and then the x squared plus 2x plus 4 in the denominator. That is your simplified fraction. All right, now we're going to get to dividing. So when you're dividing, if it's just all regular trinomials, again, factor those trinomials into their two binomials. So the x squared minus 9x plus 18 factors into x minus 6 and x minus 3. The denominator here, x squared plus 4x minus 32, factors into x plus 8 and x minus 4. I changed my division to multiplication, and then when I factor the numerator, it's going to go in the denominator, because you have to change this to multiplication and flip. So when I factor this, I get x plus 6, x minus 3, but it goes in the bottom. When I factor this denominator, it's going to go at the top, x minus 8 and x minus 4. Now that everything's factored and I'm multiplying, you can reduce things from the numerator and denominator that are identical. So then what we have left is x minus 6 and x minus 8, and then x plus 8, x plus 6. The next one, we have, again, a dividing, but we have something that is not a fraction. So whenever you have a binomial or monomial or binomial, something that's not a fraction, and you're adding, subtracting, or multiplying or dividing fractions, it might be helpful to put this over 1, so that when you change this division to multiplication and you have to flip this, you would end up getting a 1 at the top. This became, I factored out a 4, which then gives you 4 parentheses x 2x plus 1, but this numerator did not change. Here I would factor out a greatest common factor of x. So now that I've factored this and I've changed that to multiplication, I've flipped and factored, what do we have in the numerator and denominator that we can reduce? Well, the 20 can be reduced with the 4. That will leave us with 5. So ends up, looks like I've multiplied across first. You don't have to. You could reduce the 20 and the 4 right away, and the x's, the x here with the x there. Or if you multiply across and get 20x, and then the x times the 4 would be 4x times x minus 5 times 2x plus 1, then reduce. That's still going to give you 5 at the top. The x's reduce, so we just have 5 over x minus 5 and x plus 2x plus 1. Now just let me make a note. If by chance everything canceled from the numerator, so if this was, say, a 4 and everything canceled out from the numerator, you would have to put a 1 in the numerator. Just, you know, you can't just write your denominator as your answer. You have to put it as 1. It has to stay in the denominator. So factors that are left over in the denominator have to stay in the denominator. If everything cancels from the numerator, then you need to put a 1 in the numerator. Okay, number 21. So here you're finding a least common multiple. So we have 36x squared and 9x squared minus 18x. Again, to find the least common multiple, I would factor what you can. So the well, I'm going to start with the binomial first. So the 9x squared minus 18x, I can factor out a 9x. which would then leave me with a binomial of x minus 2. So the factors of this, now I could factor the 9 into 3 times 3, and I could factor the 9 here into 3 times 3 and the 4 into 2 times 2, but it's not necessary to break it down that far. Basically, your least common denominator, or least common multiple, is the greatest common factor. You have to take the greatest common factor, or whatever they have in common, times whatever your remaining factors are. So in this first problem, they have a common factor of 9 and x. So this is what they have in common. But then you have to multiply also by all the leftovers. So the 9x is what they have in common, then multiply by the 4 and x, that is left over from this one, and then the x minus 2, which is left over from that one. You do not need to multiply all of it together, but you do need to multiply at least the monomials together. So 9x times 4x would give you 36x squared, and then you'd have x minus 2. So again, factor the 36x squared into 9 times 4 times x. Factor the 9x squared minus 18x by factoring out the GCF, 9x, and then x minus 2 is left over. Your least common multiple comes from taking what they have in common, you only need one of those, times all the leftovers. All right, so then in number 22, same kind of idea. Now this should be changed on your copy to be 9x squared minus 4, and then that would factor into 3x plus 2 and 3x minus 2. And then this trinomial we would factor with AC method, which would work out to be x minus 4 and 3x plus 2. So your least common multiple contains what do they have in common? 3x plus 2. What do they not have in common? The 3x minus 2 and the x minus 4. So that's the least common denominator, or least common multiple, of 9x squared minus 4 and 3x squared minus 10x minus 8. All right, 23. Now we're adding and subtracting. So in order to find a sum, or in order to add or subtract fractions, you have to have a common denominator. So it's helpful to factor any denominators that you can factor. So this denominator can be factored into x plus 4 and x minus 3. This factor, x plus 4, cannot be factored. So the least common multiple contains what they have in common, which is the x plus 4, and then whatever the leftover is, so x minus 3. So the least common denominator is going to have x plus 4 and an x minus 3 in it. So we want both the fractions to have that same denominator. Well, this one already does, so we don't need to change this one at all. But this fraction does not have an x minus 3 in the denominator, so we have to multiply both the numerator and denominator by the x minus 3. So when I distribute that 8, I get 8x minus 24. Now combine like terms, I get 10x minus 24 over x plus 4x minus 3. Do not multiply these together, just leave them in factored form. Now if you are asked to state the domain or the undefined values, you would just say all real numbers except 4, x equals negative 4, x equals 3, or just say x cannot equal negative 4, x cannot equal 3, and again that comes from the denominators only. All right, number 24. This one looks very similar to the last one, but there's a minus sign in between. You also have a binomial here. So what I always suggest is that if you are subtracting, change this subtraction to plus and distribute that negative to both terms in the numerator. So that's going to make that a negative x and a negative 2. But then the minus is going to become plus. Now factor the denominator. X minus 6 and x plus 3 are the factors of that denominator. And that's also going to be your greatest common factor. Or not greatest common, least common multiple. Least common denominator. Yeah, I'm getting the words all mixed up. All right, so x minus 6 and x plus 3 are already factors of this denominator. So this one does not change. But this denominator only has x minus 6. So it needs to be multiplied by x plus 3. When you have a binomial times another binomial, though, you have to FOIL it out. So the negative x times the x will be negative x squared. So notice this 2x squared I brought down, but since the denominators are now going to be the same, I can make it all one fraction. So the 2x squared comes from here. The negative x times x would be negative x squared. The negative x times 3 is negative 3x. Negative 2 times x is negative 2x. Negative 2 times 3 is negative 6. Now combine like terms. 2x squared minus x squared is just 1x squared. Negative 3x and negative 2x is negative 5x, and then we have our minus 6. At this point, you always want to check to see if you can reduce this, or if you can factor the numerator. And if it can be factored, can it be reduced with one of the things in the denominator? So the last problem, the only thing I could factor out would be a 2. If I factored out a 2, it would not reduce with either one of these denominators, which is why I did not go further. But in this problem, you can factor your numerator. So, let me move this over without showing too much. So that numerator can be factored into x minus 6 and x plus 1, so then you can reduce the x minus 6 with the 1 on the bottom. And then your simplified answer will be x plus 1 over x plus 3. All right, so as far as undefined values or domain, x cannot equal 6, x cannot equal negative 3. So positive 6 and negative 3 cannot be x. X cannot equal those values. All right, 25. All right, so again, we're adding. If we factor this denominator, x squared minus 25 factors into x plus 5 and x minus 5. So the least common denominator is going to be x plus 5, x minus 5. This first fraction already has x plus 5, so we need to multiply by x minus 5. The second fraction already has both, so it will not be multiplied by anything. Distribute the 4 to the x and distribute the 4 to the negative 5. So we'll get 4x minus 20 plus that 2x all over x plus 5, x minus 5. Combine your like terms, you get 6x minus 20 over x plus 5x minus 5. Yes, we could factor out a 2, but that's not going to reduce with either one of our denominators, so it's not necessary. That's our simplified answer. And again, as far as domain or undefined values, x cannot equal positive or negative 5. For number 26, we have another subtraction problem. So I changed that negative to a positive, or changed the subtraction to addition, but put that negative in the numerator with the 2. Now I'm going to factor this denominator into x plus 4 and x minus 2, and that x minus 2, just bring it down. All right, so now looking at our denominators, this fraction already has both factors in the denominator. This one, in order to make it the same, has to be multiplied by x plus 4. So this numerator doesn't change. That negative 2 times that x would be negative 2x. The negative 2 times 4 would be negative 8. And then it's all over that same denominator. Now combine like terms. X squared doesn't have any like terms, so it's just brought down. Negative 4 and negative 2 combined is negative 6. 16 minus 8 is positive 8. Then again, can we factor this? Yes, we can. This numerator now factors into x minus 4 and x minus 2. So the x minus 2's can reduce, and you end up with x minus 4 over x plus 4. That is your simplified answer, and your undefined values or domain, x cannot equal positive 2 or negative 4. And again, those come from the denominator before you cancel anything out. So positive 2 and negative 4 are your undefined values. All right, now we get to complex fractions. So in your complex fractions, there's different ways of doing this, but I like to simplify my numerator, my big numerator and denominator. So I like to get this to be one fraction, and then the fraction bar basically means divided by, and then I try to get this to be one fraction. So let's see. Oh, okay. I'm just looking, how would I get this? So the 3x and the x squared are not like the same denominators. They're not the same denominators. So if I multiply the first fraction by x, that will give me the x squared that I need to match that x squared. But this fraction needs to be multiplied by 3. So the 4 times the x would be 4x, the 2 times the 3 would be 6, and then the 3x squared would be my denominator. This division sign is from my big fraction bar here. Now in the denominator, what was nice is that I already had the same denominator. So when you have the same denominator, you just need to subtract or add the numerators. So x minus 4, that's where I got that from. And then the denominator was x plus 1. When you're dividing, you can multiply by the reciprocal. So the x minus 4 goes in the bottom, the x plus 1 goes at the top. And then over here, I was continuing to simplify that here to a single fraction. So now that I've got a single fraction times a single fraction, I can factor out a 2 from the 4x plus 6. But again, would that 2 reduce with anything in the denominator? No. So I really didn't need to factor out the 2. So if you just had 4x plus 6 times x plus 1, that's fine. Your denominator will be 3x squared times x minus 4. But nothing can be simplified from there. Okay, the next one, so my numerator is already a single fraction, so I just brought that over. Change my fraction bar to a division sign, and then my denominator I want to make into a single fraction. So the least common denominator is going to be a product of both of those. So the first fraction needs to be multiplied by x plus 5. The second fraction needs to be multiplied by x minus 3. So now they have the same denominator. I can make it one fraction, simplify the numerator, 2x plus 10 and x minus 3, combine like terms. And it looks like I was trying to multitask here. So when I combine like terms, I put it in the denominator. So the x plus the 1x became 3x in the denominator because I'm multiplying by the reciprocal. 10 minus 3 gave me a positive 7 there, and then these factors go in the numerator. And then this one just comes down, so now we can reduce the x plus 5s. So I end up getting 3 times x minus 3 at the top, and then 3x plus 7 in the bottom. So that's my simplified fraction. All right, so now we've got our solving of equations. Now in your handout, I did revise this handout a little bit and gave a little bit more space. So a couple of these problems that are on this page are actually on the back side, but I don't think it really matters. All right, so make sure that you check for extraneous solutions. So looking at your denominators here, 0 and 2 would be your undefined values. So as long as you get a solution that's not 0 or 2, you will not have any extraneous roots. All right, so this first one here, we just have a single fraction equal to a single fraction. So in these type of problems, the easiest method to solve would just be to cross multiply. So take your 3 times your x minus 2, and then your 1 times your 4x. Distribute, you get 3x minus 6 equals 4x. Subtract 3x, you get x equals negative 6. And check it with your undefined values, you're good. You could also plug it back into the equation on both sides to make sure that it equals. Both sides give you the same value. But that is the solution. All right, number 30 is also a cross multiplication problem. That would be the easiest way. But also if you got a common denominator, you're going to end up multiplying the 2 times the x minus 1, and you'll end up multiplying the x minus 3 times the x minus 4. Just make sure when you're multiplying a binomial times a binomial that you don't forget to distribute it to all the terms. And that 2 gets distributed to both the x and the negative 1. So you should get 2x minus 2 there after you've multiplied the x and the x minus 1 together. And then when you multiply the x minus 3 times the x minus 4, you get x squared minus 4x minus 3x plus 12. And then since this is now a quadratic equation, you want to get 0 on one side, and you also want your x squared term to remain positive. So let's subtract 2x now to cancel that out. So the negative 4, negative 3, and negative 2x combine to give you negative 9x. That x squared comes down. If I add 2 to my 12, I'll get 14. So then take that trinomial, and we have to solve it, and I'm going to solve it by factoring x minus 7 and x minus 2, which gives me my solutions of 7 and 2. Are either one of those going to make my original equation undefined? No. My undefined values would be positive 4 and positive 1, neither of which is my solution, so good enough. All right. The next one now, we have, we're going to use the least common denominator to help us solve this. So 5 and x has a factor of 5 and x. 3 has a factor of 3, but 15 has a factor of 3, 5, and x. So your least common denominator would just be 15x. And the only thing that x cannot equal is 0. So the first fraction, you just need to multiply by 3. So that will give you 6 over 15x. The second fraction, you just multiply by 5x, so that you'd get a 15x. But your numerator would be 5x. So 1 times 5x would be 5x over 15x. This fraction already has a denominator of 15x, so it does not need to be multiplied by anything. And then here we basically have the same denominator now, so 6 plus 5x over 15x, we can eliminate the denominators. Now remember, you only eliminate denominators with equations. So once you've got a common denominator, the numerators have to equal each other. So 6 plus 5x then will equal 4. Subtract your 6, which gives you negative 2, divide by 5, and you get negative 5 halves, which is not your undefined value, so that should be an okay solution. 32. If you see, like before, if you see something that's a whole number or a binomial and does not have a fraction, is not a fraction, make it a fraction. Put it over 1. And then you're looking at your denominators. Your least common denominator is going to have x plus 2. It could have a 1, but it's not necessary, and x. So the first fraction already has the x plus 2, so we need to multiply it by x. The second fraction doesn't have either, so we have to multiply it by x and by x plus 2. This fraction on the other side of the equals has the x in the denominator, but does not have the x plus 2. So now that they all have the same denominator, or if we simplify, 3 times x is 3x over x times x plus 2. 5x times x would be 5x squared. 5x times 2 would be 10x. And then the 1 times the x plus 2 would just be x plus 2. Now that they have the same denominator and it's an equation, we can eliminate the denominators and write our equation just setting the numerators equal to each other. So I put the 5x squared first, added the 3x and the 10x together because they're on the same side and they're like terms. Then I subtracted x and subtracted 2, which gives me this trinomial. All right, so now what if you get a trinomial that cannot be factored? If you get something that cannot be factored, then you have to use quadratic formula. Is it possible that you could have a problem with quadratic formula? Absolutely. So your quadratic formula, negative b plus or minus the square root of b squared. I did that wrong. What the heck was I thinking? So that's going to make that change. So my b squared would be 144 minus 4 times AC, so 5 times negative 2 would be negative 10. So that would give me a positive 40. So 144 plus 40 would be 184. And then that could be simplified a little bit further. Let's see, I know 4 goes into it. So let me extend this a little bit further. My square root of 144, or 184, it can be factored into square root of 4 and square root of 46, which is 2 times 23, so that cannot be simplified. So then this is going to be 2 square root of 46. All right, so that negative 12 plus or minus 2 square root of 46 over 10, we can reduce those by 2, which would then give us negative 6 plus or minus the square root of 46 over 5. So sorry about that mistake. Yeah, so that b squared would be 144 minus 4 AC, which would be negative 10, and then we simplify from there. So the answer should be negative 6 plus minus square root of 46 over 5. All right, these next couple problems are probably on the next page for most of you with the newer handout. So in problem 33, you look at your denominators and factor that denominator. This one, denominator factors into x plus 9, x minus 9. So that is also going to be your least common denominator. Your undefined values are going to be positive and negative 9. Your first fraction already has x minus 9, so we multiply it by x plus 9. The second fraction already has the x plus 9, so multiply it by x minus 9. The third fraction on the other side of the equals already has both, so don't multiply it by anything if it already has both denominators. So this denominator, we simplify the numerator, we get 9x plus 81. To simplify the numerator here, x squared minus 9x, and then bring down that 10x squared. Now that we have the same denominator, we don't need it anymore to solve an equation. But we do want to combine like terms and put this in the right order, so put the x squared first. The 9x and the negative 9x cancel out, and then I got plus 81. And then I've got this 10x squared here. Since the 10x is bigger, I'm going to subtract x squared, which will give me 9x squared, and subtract the 81 so that I get 0 on the left. At this point, I could factor a difference of squares already right now, or I could factor out the 9 first, then factor my difference of squares. Either way, I would get a solution of positive and negative 3. The 9 does not have an x with it, so there would be no solution with that 9. It's just an extra factor that gets factored out. So your only solution is positive and negative 3. And then double check. Would either one of those make your denominators undefined? No, my undefined values are positive and negative 9, not positive and negative 3. But always check that. All right, 34. Now we have a minus sign. So once again, I would suggest that you change your subtraction to addition, but then that negative needs to be distributed to both the x and the negative 1. So that's going to make that a negative x and a positive 1, and then change that to plus. When you're looking at the denominators, your least common denominator is going to be a product of x minus 4 and x plus 4. So the x over x minus 4 has to be multiplied by x plus 3. The second fraction needs to be already has x plus 3, so multiply by x minus 4. Then equals the negative 4 over x plus 3 has to be multiplied by x minus 4. Simplify your numerators. X times x will be x squared. X times 3 will be 3x. The negative x plus 1, that when you're multiplying a binomial times a binomial, make sure you distribute it to everything. So negative x times x is negative x squared. Negative x times negative 4 will be a positive 4x. 1 times x will be positive 1x. 1 times negative 4 will be negative 4. And then on the other side, negative 4 times x is negative 4x. Negative 4 times negative 4 is positive 16. Now combine like terms. So what's nice here is the x squared and the negative x squared cancel out. Your 3x plus 4x plus 1x will be 8x. Bring down your minus 4. And then bring down the other side. I added 4x to both sides, got 12, and then added 4 to both sides to get 20, divided by 12, and reduced and got 5/3. So once again, if I check with will 5/3 make my original equation undefined? No. So 5/3 is an okay answer. There will be one of them that has an undefined value somewhere. Maybe not. Maybe we need to add that to our, we should probably add that to our review. Maybe I'll add one in class. All right, so then 35, you have f of x equals 1 over x squared minus 7. So this one is similar to the graph of the ones that just had an x in the bottom, but now we've got an x squared. So again, looking at the denominator, your undefined value would be 0, so your vertical asymptote is going to be x equals 0. So using that vertical asymptote, plug in some numbers that are to the left and to the right of 0. So I used negative 2, negative 1, positive 1, positive 2. And then the minus 7 means that your horizontal asymptote is going to shift down 7. So y equals negative 7 is your horizontal asymptote. When we plug in your negative 2 or positive 2 for x and you square it, you're going to get 4 either way. So that's going to equal 1/4 minus 7, which is negative 6 3/4. So whether you're substituting negative 2 or positive 2, you're going to get the same thing. I don't know if I showed that over here. Oh, this is finding the inverse. Okay, that's right. We have to find the inverse. And then if you plugged in positive or negative 1 and square it, you're just going to get 1 minus 7 would be negative 6. So then I graphed those points, negative 2, negative 6 3/4, negative 1, and negative 6. So we have this side getting closer to the vertical asymptote this way and the horizontal that way. Then we've got our positive 1, negative 6, and positive 2, negative 6 3/4. So again, we have that. So this would be our graph of this equation. Well, if you're asked to find the inverse, your f of x is basically y. So your y becomes x, your x becomes y, but everything else stays the same. Now we need to solve for y. So add 7, which will give you x plus 7, and then multiply by the y squared to get it out of the denominator, and then divide by x plus 7. So at this point we have now y squared equals 1 over x plus 7. You've got to get rid of the square by taking the square root of both sides. Because it's an even root, though, you're going to have a positive and negative root. So y equals positive or negative square root of 1 over x plus 7. So that would be your inverse equation. So then it asks determine whether the inverse is a function or not. So by using the horizontal line test, we could see that it's going to, if you use the horizontal line test, it will cross more than one point. So the inverse, this function here, is not a function because the horizontal line test would intersect more than one point. All right, so then we practiced finding some more inverses here. So again, g of x is basically y, so change that to x, change your x to y, but the 2 in the numerator that would be the same, the 3 in your exponent stays the same. To get that y to the third out of the denominator, multiply both sides by y to the third, then divide by x, and then take the cubed root of both sides. Since you have an even root, you do not need to worry about the plus or minus. It's just going to be y equals cubed root of 2 over x. In the next problem, again, make this x, make your x y, subtract your 5, which will give you x minus 5. You could, and then, well, I just switched my numerator and denominator. So that's one way of, when you have proportions, in order to get the y to the fourth out of the denominator, you can switch the numerator and denominator. We could have done that over here. So right here, I could have put the x on the bottom and the y to the third at the top, and then skipped this step altogether. So if we look at from that step to this step, you can kind of see how the x went to the denominator, the y to the third went to the numerator. So you can do that with proportions. So that's basically what I did here. I moved the x minus 5 to the denominator, moved the y to the fourth to the numerator, and then my 3 is still my numerator here. To get rid of the fourth power, I take the fourth root. Again, it's an even root, so don't forget plus minus in front of that fourth root. And then the 3 over x minus 5 is all in the denominator, or all in the radical. All right, so that is your end of your review for Chapter 6. Good luck on your test.